So before we get to graphing our rational functions, that's going to be our end goal. We'd like to also find intercepts. Now, y-intercepts, those are going to be the easiest. That's going to be when x is equal to 0. Nothing special, just simply plug in x equals 0, simplify things, great, you'll find your y-intercept that way. X-intercepts get a little bit trickier because this is going to be where we set y equal to 0. So we want to set our entire function equal to 0, but because it looks maybe a little crazier than you're used to seeing, this requires us to be a little bit careful, especially because holes might cause an issue. So if we take a look at this example, I give this to you already in factored form. That will just help us a little bit here. But remember, x-intercepts, we set y equal to 0. For y-intercepts, set x equal to 0. For x-intercepts, set y equal to 0. To do this properly, we want to use the simplified expression after factoring and canceling. Because you like to just factor and cancel when possible, we're going to use that for most of it. That's going to be, once it's factored and canceled, we're going to use that for our vertical asymptotes, and we're also going to use that here for our x-intercepts. So if we take a look at what the math will look like, is we see here that we can cancel, right? We can cancel the x plus 2 in both of this. So we're left with x plus 3 divided by x minus 1 times x minus 5. So just as a brief rehash, we see that x equals 1 and x equals 5, those would correspond to vertical asymptotes. We see that x equals negative 2, that makes both the denominator and numerator equal to 0. That came from our cancel term. That's going to be where a hole is located at x equals negative 2. Also, as a little reminder here, the degree of the denominator is 3. The degree of the numerator is 2. So when the degree of the denominator is larger than the numerator, that gives us y equals 0 as a horizontal asymptote. So y equals 0, horizontal asymptote, when the degree of the denominator is larger than that of the numerator. Okay, but back to looking for x-intercepts. So what we now have to do is we have to set y equal to 0. Now remember, y is just another way of describing this. So I am solving 0 is equal to x plus 3 divided by x minus 1 times x minus 5. Now when we have a fraction equaling 0, the only way for this to equal 0 is if the numerator equals 0. We know both of them won't equal 0 at the same time because we've already canceled them. But here, if we try to set the denominator equal to 0, well, that doesn't make anything equal to 0, right? A number divided by 0 is undefined, but 0 divided by a non-zero number is equal to 0, right? 0 divided by 5 is 0. 0 divided by negative 7 is 0. So all you do is now you set the numerator equal to 0. So you have 0 is equal to x plus 3, so x is equal to negative 3. So this says that we have an x-intercept at the point negative 3, 0. So remember, intercepts are points. So when y equals 0, our x value was negative 3. And so this is the only x-intercept. Now, x equals negative 2 made the original numerator equal to 0, but there's a hole there. So there would just be a big opening at the point over here at x equals negative 2. It's not truly an x-intercept. So just be careful. Make sure we're using the simplified version. Then only set the numerator equal to 0. Numerator equals 0 of the simplified gives us our x-intercepts. The denominator set equal to 0, those are going to be vertical asymptotes. So be careful. Make sure you know which one set equal to 0 gives you which piece of a rational function.